Hello everybody, and this is the GC Surgery Session 6 entitled GC Lag Time Calculation. This is a recording of the session which was presented on the 17th of May 2016. First of all, a bit about spot sampling. There are various reasons why we take a spot sample. The spot sample results can be used as keypad values in the flow computer in the case of a GC failure. Also, the spot sample analysis can be used to update the heavy end split in the flow computer. In other words, all the components from C6 and above, from hexane and above. The GC may measure all these components as one, but the calculation of energy needs the individual values, especially at the heavy end, as that's where all the energy is. It can also be used to update the isentropic exponent and dynamic viscosity for flow rate prediction calculations. And also you can compare the spot sample analysis to the GC result, and we'll see later on how useful this can be. So it's quite important to get a good spot sample. Here's an extract from the UK measurement guidelines, the latest guidelines, saying that a manual sampling points should be provided, and these should give representative samples. The spot sample is typically taken just after the sample probe, and so that will be at line conditions. There are various methods of taking a spot sample. These are all described in the ISO 10715 standard, but it's important to have a good method and a good procedure to make sure the spot sample is representative of the actual gas in the pipeline. There's sometimes a risk of taking a bad sample. For example, there's a risk of air contamination, especially if you're using the purging method. Now on to the sample letdown system. The operating gas pressure is significantly higher than the operating pressure of the GC. For example, the line pressure may be at 100 bar, whereas the safe pressure for the sample gas to enter the GC is usually around 3 bar. So we must reduce the pressure of the sampled gas before it is analysed. For this reason, we use a sample letdown system, which provides pressure reduction. In the ISO 10715 standard, it states that the temperature will fall by ½ degree C per every 0.1 megapascal during the pressure reduction, and this is due to the Joule-Thomson effect. So this can be quite a significant fall in temperature when you're talking about reducing the pressure by up to, say, 100 bar. Therefore, we must apply heat to avoid liquid dropout of the heavier components. The sample letdown system is therefore a series of stages which comprises pressure regulators, heaters, pipes and tubing of various sizes, pressure and temperature indicators at each stage. There may also be a bypass flow. The bypass flow is gas discarded in between stages. This is used to reduce the volume and also increase the flow, and so quicken the time that the sample reaches the GC from the point that it's actually sampled from the pipeline. And this takes us on to lag time. So what is lag time? Well, lag time is quite literally the time from A to B, where A is the point where the gas is sampled from the pipeline, and B is the point where the gas is analysed by the detector, or in other words, when it goes through the GC detector. It's important to have as fast a lag time as possible Because if the lag time is long, then if there is a problem or a disruption in the pipeline, you won't know it until the gas is analysed, and this may be for quite a considerable time, even up to hours. So the faster the lag time, the faster the response to a problem. Also, if we know the lag time, then we can do a more realistic comparison of the spot sample versus the GC result. Now, times must be calculated for all stages having different conditions, so that's anything affecting the volume or the flow rate at that particular stage. This particular sample letdown system that's illustrated has 3 stages of pressure reduction, so that will be 3 different pressures and 3 stages. But as well as that, we have to consider first off the sample probe as one stage, and then the sample probe to the first regulator. So that's assuming that the sample probe will have a different volume to the tubing between the probe and the first regulator. Then the third stage would be the first pressure regulator to the second. The fourth stage would be the second pressure regulator to the third pressure regulator. The fourth stage would be the third pressure regulator to the GC itself. And then finally, of course, we have to take into account the total GC analysis time from the point where the gas, the sample enters the GC to the point where the gas is actually analysed at the detector. So we have to consider all these stages when we're calculating lag time. The bypass flow affects all of the stages previous to that bypass, and so in this case it will affect the first 4 stages and have to be included in that in the lag time. So how do we calculate lag time? Well, I'm going to present a method here which is quite a simple method, and it's all based on well understood physical principles. Travel time, of course, is volume over flow rate. Now the flow rate for each stage that we're looking at will be the sample flow plus the bypass flow, which affects that particular stage. Now, because both typically will go to atmosphere, these flow rates can be assumed to be at standard conditions. And so in order to calculate the time, we must convert the volume at each stage to those same conditions. So we must convert the volume to the standard volume. To do that, we use the ideal gas law, which I'm sure most of you will be familiar with. So we can express this ideal gas law at any conditions we like. So for example, first of all at standard conditions, where P1 is standard pressure, T1 is standard temperature. And then at line conditions or at any other stage having a different pressure and temperature. We can rearrange these equations because we have the common values of N and R there. So we can rearrange these equations to derive an equation for V1, which is the standard volume, using the volume at other conditions as long as we know the temperature and the pressure and the corresponding compressibility at those other conditions. So this is how we can convert the volume at any of those stages to standard volume. The time then at each stage is that standard volume divided by the total standard flow rate at that stage. There are a few inputs which are common to all stages. So that is the standard temperature, standard pressure, the corresponding compressibility at those standard conditions, which can be calculated, for example, from the AGA8 standard, and then also the sample flow, which is of course common to all stages. I have here an example calculation then which I created in Excel. So we have the inputs which are common to all stages at the top. And then each stage we have to enter 6 inputs. So that is the temperature and the pressure at that particular stage, the corresponding compressibility, which we can find from the AGA3 standard, for example, the tube size, or the tube internal diameter at that stage, the length of the tubing at that stage, and also we have to include the bypass flow when it affects that particular stage. From there we can calculate the volume at those conditions, and then from the volume at those conditions we can calculate the standard volume using the formula which we just derived. Once we have the standard volume, then we can find the time at each stage by dividing the standard volume by the total flow, which is the sample flow plus the bypass flow. The bypass flow, of course, being only relevant if it affects that stage. So going back to the previous example, first of all, stage 1 is the sample probe. So we have the line temperature and line pressure, corresponding compressibility, the tube ID, which is the thickness of the sample probe, the length of the probe itself, and we have to include the bypass flow at this stage also. So the volume of the gas at this particular stage is simply the pipe area, or the sample probe area, multiplied by the length. The standard volume then can be calculated using the formula we derived, and then the time is simply that standard volume divided by the total flow, which is the sample flow out of the GC plus the bypass flow. So this is the time which is attributed by this particular stage, which is the sample probe. The second stage then is the sample probe to the first regulator. In this case, the temperature and the pressure are the same. There's been no pressure reduction, so it's the same compressibility, but the tube internal diameter is smaller, and the tube length in this case is 100 centimeters. We still include the bypass flow, and so calculate the volume at these conditions in the same way, and also the standard volume using the derived formula, and the time is the standard volume divided by the total flow. So this particular stage contributes 8.6 minutes to the total lag time. The third stage, so you would have a temperature indicator here telling you the temperature at that point, and also a pressure indicator. So the pressure has gone down. There's a different corresponding compressibility. The tube ID is the same as the previous stage, or it may be different, but in this case it's the same. The length of the tube in this particular stage is 10 centimeters. We have the same bypass flow, and so using the same calculations we can calculate that the time attributed to the total time at this stage is 0.36 minutes. Stage 4 then, again we would have a temperature indicator telling us the temperature at this stage, and the pressure, again this has reduced. The line compressibility then increases as the pressure reduces. The tube ID at this stage is the same as the previous stage, and we have a length this time of 100 centimeters. Using the same calculations then, the time attributed to the total lag time at this stage is 1.39 minutes. So stage 5 is the third pressure regulator to the GC. So there's been a further drop in pressure, so this now makes it safe for the sample to enter the GC. Line compressibility again has been recalculated and has increased due to the drop in pressure. The tube ID is the same as the previous stages. At this time the tube length is 1300 centimeters. the bypass flow is no longer applicable at this stage. So using the exact same calculations, then the time towards the total lag time at this stage is 16.2 minutes. We then of course have the total GC analysis time, or the cycle time, which is dependent on the type of GC and also on that particular GC's configuration. But I've put a time of 4 minutes in here, which is typical for, say, a C6 plus GC. We then simply sum all of these times and can calculate the total lag time, or can estimate the total lag time, in this case to be 31 minutes and 58 seconds. So going back to my previous comment, which is the lag time should really be as short as possible. In this case, you can see that the GC analysis time is 4 minutes. And so this isn't really ideal, because the GC will not be getting a fresh sample every time. We've seen some elements of the GCAS software in previous sessions. I just wanted to mention that the GCAS software does include a built-in lag time calculator, and so it's exactly the same method as I've just described. So we have the global parameters, which are common to all stages. We then have all of the pressure letdown stages, so you can add more stages in here, and you can remove stages if they're not applicable, and then the GC time, and this will calculate the total lag time exactly as I've just shown. So the example that we've just seen, a lag time of over 31 minutes, is not ideal for a GC with a cycle time of just 4 minutes. We can reduce the lag time. We can use a smaller sample probe, for example, to reduce the volume there. We can use shorter lengths between stages. This has a particularly higher impact when the pressure is higher. We can use smaller tubing. Again, this has a larger impact when the pressure is higher. The standards dictate that we should not use less than a 3mm tubing. We could also increase the bypass flow, because that then reduces the volume and increases the flow, and so increases the total lag time. But we must be careful how much bypass flow there is, because this can be unaccounted for gas. It's often just vented into atmosphere. And also, the higher the bypass flow, the higher the energy transfer and the more heating is required. So it's important to really design the pressure letdown system properly to begin with. But you can modify the existing pressure letdown system to try and reduce that lag time. So just want to go back to the example that I gave. In this case, the total lag time, 31 minutes, 58 seconds. If we were to increase the tube length on the second stage, so from the sample probe to the first regulator, if that tubing is a lot higher, say 1,000 centimeters, then the total time is increased significantly. This has a higher impact at this stage where the pressure is high. Going back to the first example again, if we instead reduce the tube ID, so from 0.6 of a centimetre to 0.3 of a centimetre across all of these stages, and also if we slightly reduce the length of the tubing from the third regulator to the GC, we'll see that the total lag time has decreased significantly. So you can make a big difference by redesigning your sample letdown system. Now I just want to introduce how useful doing a comparison of the spot sample analysis to the GC result can be. We've seen some methods described in previous GC surgery sessions on how to know that your GC is healthy to begin with. So if you know that your GC is okay, then any discrepancy in a spot sample versus the GC result means either a fault in that spot sample itself, or in the pressure letdown system, meaning the GC is not telling you is analysing something which is not the actual gas in the pipeline. So in either case, it's not a good thing. We really need that spot sample to match the GC result. Some things to look out for is the nitrogen level to begin with. If the nitrogen level is not similar, then this is an indication of air contamination, which I said can be typical when taking a sample, especially if using the purging method. Also, you really need to check the heavy ends. If the heavy ends are not similar, and if the heavy ends in the spot sample are higher than that of the GC analysis, then this is a big indication of liquid dropout. To identify whether the two samples, the spot sample or the GC analysis, are similar, we can apply the reproducibility limits as given in the ASTM D1945 standard. I wanted to share with you a real case study, and this is of heavy end dropout, which was discovered using just this method of comparing the spot sample analysis to the GC output. And this detected the heavy end dropout, which was actually costing the operator £100,000 a month. We were able to quantify this by calculating the difference in CV. This issue was present across 3 assets, which amounted to £500,000 a month error just for this one operator. Now, this is a nice introduction to the next GC surgery session, which will be session 7. And we hope that you'll enjoy that session as well. So thank you very much. If you have any questions relating to this recording, to this presentation, then please post them on the GC surgery group on LinkedIn. There are already some questions and answers posted in the LinkedIn group, which we hope you'll find interesting. Or if you have any queries which you'd rather not post on the LinkedIn group, then please contact us directly. That's myself, Jennifer Rabone, and Anwar Sultan of i-Vigilant, and we'd be happy to answer any questions you have. Thanks again for listening.